Hi. Um, you all must have heard about ChatGPT and other chatbots that's been popping up these days. The big brain behind those uh, applications is a large language model. Large language models are good at generating human-like text, but when it comes to uh, formatting, giving a formatting output, it fails. Sometimes in our application, we need to have a formatted output, a polished output, instead of this large natural language that this LLM gives us. In this presentation, we will talk why we need such a polished formatted output and what are the things that we can do to get such output in Python. Okay, let's start the presentation. My name is Ramesh and I'm the co-founder and CTO of Fcode. We are a software engineering company based in Colombo and Sri Lanka and Singapore, and we've been developing applications in different industries like manufacturing, energy, textile, and healthcare. With the knowledge that we got from healthcare domain, we have implemented our own application called Progress Magic. It just uh, finished its alpha testing stage, and we are moving to beta testing these days. And if you need to know more about this application, you can go visit our website in the QR code here. Okay, let's talk about today's agenda. We will first give an introduction to what prompt engineering is, and we'll introduce Pydantic, and we will try to implement some prompts with Pydantics, and we will go to advanced prompt engineering techniques and try to implement them with Pydantic. So for all these implementation, I will be using OpenAI's API, but it can be modified to work with any uh, LLM. So what's prompt engineering? It's basically designing and refining input prompts for the LLM. What that means is we start simply by creating a simple prompt for the LLM, and we observe its output and we increase the complexity of our input such that it will give a better response the second time we attempt. So we have to test different variation, and while testing you will see that minor changes to the prompt can result in very different outputs in the model LLM's output. These are basic components that should be there in LLM that are good to have things. If you talk about types of prompt we have, basically we can categorize them into three categories. First one is one-shot learning, where we just ask something from the LLM and it will give a response to us. Uh, zero shot prompt, and the second one is one-shot prompt, where we send an example with the prompt, and the LLM will try to analyze the prompt and the example and generate output. The one-shot method we basically use when we need to format our response in a certain way. Uh, and the third one is few shot learning. We send few examples along with the prompt, and it can be used for like teach new things for to the LLM. Here's example that I tried with GPT chat. I give bunch of text with different labels, and LLM try to label, recognize the pattern and label the last text. So it has clearly said that it is a negative state, and we can see in the people are doing different kind of modifications to this prompt, like by changing the output label, uh, randomizing the labels, giving wrong data, things like that, doing things like that. They try to test the uh, behavior of the LLM. You can watch lots of them in the YouTube. Uh, we'll talk why we need the formatable output. First thing is the consistency. When we get the output from the LLM, uh, for the same query, the LLM will give different outputs every time we run it. So there's the problem of consistency, and data handling is very hard. We have to either handle data manually, or we have to write a script to handle data. If we do that manually, uh, we have to copy the data we need to the application by our hand. If we are using a script, we have to read the whole text given in the LLM output and find patterns. It's going to be lots of if else and switches statement. So such a complex logic will ultimately uh, give a error-prone code, and that such algorithm is going to be uh, very process heavy, and data integrity issues can also be there. Like, let's say I need to get uh, a out data output from the LLM. So LLM always gives me the data as the ISO string. So one day the LLM might get a new update and it will give date in another format, like let's say epoch time. It can happen. So data integrity issues are also there if we uh, rely on the just output of the LLM. So benefit wise, it will enhance the data quality. Quality means it will give a reliable output and also uh, very accurate output. These LLMs we use them as a separate system. So we have our own system in our companies, and we need our LLM to be an intelligent system that can be worked with in-house other system. We are not using it as a text generation, but we only need the intelligent part of that LLM. So LLM should work as the existing application, existing system in our large application. So usually how application communicate are based on JSON or XML. So natural languages are not used to communicate between systems. So our LLM should also work as uh, that kind of application if we need to directly integrate with that our system. Uh, and also it's going to simplify data analysis, because if we have a formatable output like JSON, we can directly pass it to a Python object, and we can do data analysis there. So we have been working with Python objects since beginning of Python, and the process can be automated with Pydantic and data classes. So those are libraries that do JSON validation and serialization automatically. And if we are using a framework, most of the frameworks have inbuilt JSON parsers. We can make use of them also. We'll go to the simple example that we can do with LLM. Here I have a data type. I need the LLM to generate random 100 data points from that data type. This can be used for a task like synthetic data generation for ML application or software testing. We need a lot of data for test application. If we have a feature like analytics in, so we have to generate synthetic data. For that, we can make use of the LLM. With the data type, we send the LLM query. Give me a list of 100 data points that will match this data type. We send that query to LLM, and LLM will output JSON object. we pass this JSON object according to the data type we have, and we have our required uh, Python objects with us. The somewhat complex example here, we don't need here we don't need data, but we need to perform some actions. In this case, we have three actions in the system. When user query something, we need to find out what's the next action to execute. So instead of guessing it, we use LLM to find the best action. In the LLM, with the user query, we send the system actions available and ask the LLM what is the next action to execute in this scenario. And LLM will give a JSON output, and we send that to an action handler in the system. And action handler look at the query and execute the system actions available. We'll go to the implementations of these things later in this presentation. Okay, so we can get JSON output from LLMs, but uh, although we are getting a JSON output, it doesn't mean that it's going to be consistent. So the same problem we had earlier is going to be there as well. The output is going to be inconsistent, and there can be unexpected formatting and incorrect data types. Partial responses can be there. Here's the example of a response I got with ChatGPT 3.5, not the API, but chat interface. So you can see that there are a few missing parts. Then why not we move to the JSON mode of the LLM? JSON mode is available in some LLMs, like OpenAI LLM has that. Google Gemini has that. Like some LLMs have that. We can do that, but only the main problem is we have a very limited control over the data structure. We can't do complex data structures like nested data structures or looping data structures or validation and parsing. We don't have a very complex, we don't have very control of error handling is done in the LLM side, not our side. And complex data relationships cannot be represented with these things. Also harder to maintain because instead of learning the programming language, we have to now understand this JSON bond also. And let's say I need to change the variable name, I have to go through all the JSON and change the variable name everywhere. So it's going to be a big mess if we are using it at a big scale. So JSON mode is not going to work most of the time. So we can use a library like Pydantic. Pydantic is Python data validation library. It uses Python inbuilt type annotations, and also it has their own type the runtime time checkers. We can write validators for fields and models, and we can customize them as any way we need. It supports complex data structures, all those things like uh, nested and looping structures, and all those things are done through code. So we always work with code, so it's easy to maintain and change anything if we need. And this support automatic schema generation. We need the schema of our Python data model, we can do that automatically. And Pydantic is very popular. As you can see, it has 9.9 over 19K stars in GitHub and over 7.5 million downloads daily. Pydantic also is very high performance. It's somewhat old and is being used in many production applications, and it supports many frameworks and libraries out of the box, like Fast API, it automatically support, and we can make it work with the models frameworks like Django or any other frameworks. Django has an inbuilt JSON parser. We can replace that with Pydantic easily and configure to work with many applications. Here's an example in schema. Uh, Here I have written a class for employee. Employee class I have put doc, uh, documentation for the class, and also I have 4 fields: ID, name, position, and subordinates. And all the fields I have put descriptions explaining what that field is. And if we generate a schema with this Python class, it's going to have all those comments, all those documentation and descriptions in the schema. And we can add extra field to the schema uh, by having a config inner class, and inside this variable we can, inside the JSON schema extra variable, we can define what are the extra things that we can attach, that we need to attach to the schema model. Here I have attached the example. So the process here is we are going to use Pydantic to generate a schema for us. So just saying I need the JSON output to the LLM will not work. We have to give a clear instruction what's going to be the output look like. So what we do is we generate a data model with Pydantic with with all this information, and with our prompt we send the scheme of this a class. The LLM understand what it needs to do, and it generates a JSON output according to this scheme. So that's how it's going to work. And here, how we going to get the JSON schema from a Pydantic model? We just call model JSON schema, and it has a pretty good schema explaining the what class does and what are the data types and what are the required data types, and descriptions of the data types are also there, and the example is also there. So everything is going to be in the schema. So we send this schema along with our query and tell the LLM to give the output of to our query according to this scheme, and LLM going to generate JSON according to this scheme. Setting up Pydantic is very easy. You can quickly install it, or you can use any other Python package managers that you use. And validation also very easy. It has automatic type validation. In this example, in as the user field, I have put a string, and in the ID you can see it as identified as a, but lots of these static errors we can omit and run the application, because these are static checks not done runtime. But Pydantic handle that runtime also. If we run this application, we are going to get a validation error. And after the JSON is being given to us by the LLM, we need to convert it back to a Pydantic model so that we can work with it. What we do is we pass it to a JSON parser and initiate our Pydantic model with the JSON values, and it will give us the model we need. So if I tell the process again, what we do is we get the user prompt, and attach the schema we need with the prompt, and send both to the LLM saying that we need the output of this query in the JSON schema we send, and the LLM will give a JSON output, and we pass that output, and load it into the schema we have, Pydantic model we have. And I'm going to introduce another library called Marvin. So that process that I just described is repetitive work. Marvin library is a wrapper for that work. That means it automatically, if you send a prompt to the Marvin, it will automatically generate that schema from our prompt, and it will send it to the LLM and get the output back as a Pydantic model. Configuration also very easy. We just have to put the OpenAPI key and the module that we are using to the configuration, and it will going to work. Now we currently only support OpenAI API, but if you need to work with other APIs, other LLMs, Instructor is a very good alternative. It's been around few years now, and it supports many languages also, not only Python. But for in this presentation, I'm going to cover everything with OpenAI API, so I stick with Maven. Maven is better for OpenAPI. When we are working with Maven, not only text, we can work with images, audio, video also. But we are focusing only on text here, and it has inbuilt working modes that we can use. Like for classification, we can directly use a Marvin inbuilt method. Classification means if we have a bunch of text and bunch of labels, we can use this Marvin method to classify the given text to the labels. And transformation, that means if we have a description about something, let's say a description about a person, we send the description of the person and the schema of the person to the Marvin function, and it will extract the data from the text and create an object for us. And data extraction also same thing, but few additional things are there, but the same functionality. And text generation means if we give a schema to the generation function, it will generate a random data uh, using LLM. And AI function is we can define a function in our Python code, and Marvin will use LLM to get the output of the function. We'll cover all those things in this presentation. Here's a simple text generation example. I have a product class with the name, price, and the description. I have explained what the product does in the docstring, and the name, price, and the description uh, have separate description in the field, and I'm sending it as the target in the Marvin generate function. And in the Marvin generate function, for the instruction, I send top mobile devices in 2015, and I need 4 of them. When I run that, it will generate 4 products using the LLM. So all those products are Python objects. Uh, if you print that, you get this result. Same thing we can do with Marvin functions. So I write this get product function. I have to send the number of products I need, and it will return a list of products. And in the docstring, I had add the template n as a template. Pydantic it automatically replace this n with the real number I sent, and I just wrap that method with marvin.fn. Marvin.fn. After I wrap that with marvin.fn, I just need to call that, uh, and it will generate the same exact same output. A little bit differences because LLMs are uh, not going to give the same output same every time. So it's how we use Marvin function. is how we can use uh, another example of Maven generate with nested models. Here I have represented a member in an organization, and all members have subordinates, and third level users don't have any subordinates. In the level field, I have written this constraint that level must be greater than or equal to 1, but should be less than or equal to 3. And all the subordinates uh, are also user fields. So it's a nested looping kind of data structure. And I'm using generate function again with prompt. I need the organization hierarchy of a small startup, starting with the CEO. And it understands that CEO means the number one source level uh, user, and generate Sophia in the first level, few subordinates with few subordinates, and those subordinates also have level 3 subordinates. And you can see level 3 subordinates doesn't have any users with them. So it completely adheres to the constraints I put in the module. Uh, so these data Pydantic of data classes are just Python classes. We can treat them how we treat to any Python class. We can add functions, properties, anything we need. So here I have written a function and a property. Now the model represents the prompt using docstrings and descriptions, and the model can contain some data in the variables, and with the function the model will represent the behavior of the uh, data model. With this schema quality and prompt quality and the data quality are kind of working together. But this is happening at the expense of good variable names, good descriptions, and good docstring. But anyway, in a good software, we should have these things, good variable names and descriptions. We should have them anyways. Let's write a custom validation with Pydantic. Here I have a user model with a username and a name. I have written a validator for username, saying that username should be between 4 to 8 characters and should be alphanumeric. But in the username description, I have not put something like that. So schema doesn't have that information, and LLM going to generate ROM username. Validation handling is not there inbuilt in Maven. So I have to write this function. If you are using instructor, it has a feature called max retry that we can use. So it will retry multiple times if validation error occurs. But here I have written a while loop that runs until we get any user. Inside that, I attach the errors to the prompt and run the prompt. If the prompt get validation error, I just update the variable with the errors. If I run that one, I get a validation error the first time. It generated the 𝘄ಗ್ಗೆ99 as the username, but it's longer than 8 characters and it has underscore. It is not alphanumeric. So it's going to send this error message also to the Python to the LLM, and LLM understand this notation and send correct output. The second time the loop runs, it has given the correct user. So when working with validations, we can use LLMs to validate our data. In this example, I have a friend schema with a name and a comment. I have written a validator for comment, which checks the value of the comment using the classify method, inbuilt classify method of Mavi. So it's going to classify whether this comment is a positive comment or negative comment. If it is a positive comment, I will raise a validation error saying that this comment must be negative. And in the same loop, I run this application, and being LLMs are trained to do positive things, first time it generate a positive comment. And so the input is chat generator is the comment is an amazing listener and always there when you need her. But that Marvin identify it as a positive comment and throws a value error. And this error is going to feed to the LLM the next time, and the next time it has negative comment. You can see uh, the comment is always complains about small things and never on time. Okay. So how to handle nullable content? Here I have a user with name and year, born year, and I'm using the Marvin cast method. That means if I give a description and the data model, it will extract the information from the description and create a Python object from that model I sent. So here the person is 49 when he married in 2007. So with that, it's going to calculate the born year and store it correctly. You can see in the output in the large image. And in the second example, I have written just random text and it doesn't have any user information. Because of that, it returns an error. It stores an error. We can simply solve this by using a try catch, but controlling the flow with try catch is a bit messy. Some people don't like that. So we can use something like maybe monad from functional programming. So maybe monad in functional programming comes to double open programming as null content, the optional fields in Python. Here I create a separate class called user response, and in the side user response, I have a variable to store the user, and it's the optional field now. And I run the same example here, but instead of user as the data type, I put the user response. In the output, you can see instead of the error, I got another response. And we can use it in Python like this with AND operation. It's basically user is there, I think its name. We can do things like that without breaking the flow. If you go to the instructor example, the same example is there, but instead of user response, they are using a class called maybe user. So it's exactly what maybe monad do. You can try that way also. Okay, here in addition, we are storing the connections of the users. That means a user can be connected to any other user with their ID. And in the 70 line, I have written that field to store the list of IDs that people have connected. And again, using the Marvin generate function, and it has generated 4 users. You can see the consistency that user 1 is connected with user 2 and 3, and you can see both user 2 and 3 is connected to 1. Consistency is maintained. And one note I need to make here is all those examples, all previous examples, and almost everything in this presentation, I use GPT 3.5. Special instances I use 4, I will tell them when they are in their slides. Here's another example. I run with a user model with name and age, and I send the request to Marvin.cast function as John is a user who was twice my age 10 years ago. I am now 40. and LLM has to identify the information of the user and create the object for it. Your name, it's obvious, but the edge has some calculation. If you run this in GPT 3.5, it gives this wrong output. So 10 years ago, the person John is 30, but now he should be 70. We do the calculation, but LLM output is 30. So in a scenario like this, instead of moving to GPT-4, I have done is write the additional field in the user module called reason. And in the description of the reason, I said that break down the provided information and explain a step-by-step process of calculating the age field. So without just generating the age, LLM will reason the algorithm that it ran behind the generation of age. This time, after running the application, you can see that the age is correctly identified as 70. So without changing the model, we can make the LLM little bit intelligent by just saying it to explain what was your thought process. Uh, so this method is called chain of thought method. This was introduced in this research paper. You can take a look. It's a little bit long research paper. Uh, we'll go to another example. Here I have two data types, addition data type and a multiplication data type. Addition data type take two variables a and b, and if I call the calc function, it will add those variables. Multiplication, same thing, but I will multiply the variables. So in addition to the uh, simple explanation of the model in the docstring, I have provided three examples in each case. Uh, so I have given simple addition expression and how to add three numbers. So it's going to have an inner object. So if I add 3 plus 4 plus 5, it's going to be addition of 3 with another addition, and that addition has 4 and 5 as A and B. So multiplication also same. I have given a few examples, uh, addition and multiplication examples. And the chain of thought, uh, for the chain of thought, I have created this mathematical expression class that will convert a given string expression to a nested set of addition or multiplication objects, and the LLM have to describe what it did in order to convert uh, the mathematical string to the set of objects. And again, I have the calc function, just calling the expressions calc function, and written the function to convert the given mathematical expression in a string to a mathematical object, mathematical expression object. And I call it with a long mathematical expression. It has brackets, and inside the brackets also there are expressions. And result I print by calling the calc function. This model I actually run with GPT-4, not GPT 3.5. You can maybe tweak the description a little bit and make it work with 3.5 also. So if we run this model with GPT-4, it's going to generate this output saying, so explaining reasoning, it gives like we have to follow Botman's rule. That means we have to solve inside the bracket first, and in that also we have to first multiply 2 by 3 and does explain the whole process. And given the expression also, it's a big addition, and uh, inside that there are nested multiplications and other addition operations. And if we print the result is correct, the result is 35. And we can run this example multiple times to make sure that the result generated is valid. It's called this code self consistency, where we run the same thing multiple times and validate the result with the uh, best answer. It's given in this research paper. You can have a look. Now we send a subtraction and division operation. Previously, not in even in the example, we didn't introduce subtraction and division. But if we give an expression like this that have divisions and subtraction, it's going to correctly reason what's happened, and it have given the correct object representation also, and the output also correct, which is 7. These kind of applications, these kind of things we can use in many type of application where we need to split our task into smaller tasks and nest them. So for application like business process automation or a ETL task where we extract, transform, load task, and even in code analysis task. So code means just inside file we have functions, classes. So it's a we can represent in a nested way. So all those kind of things we can model using these methods and try to get some solutions with the use of LLM. Okay, here's a summary of things we learned so far. We just use directly getting the output from the LLM with a few shots, zero shot prompting, and we introduce chain of thought. We just get the reason behind and step-by-step process of generating that output, and it's going to perform better. And that about consistency where we run the COT multiple times and get the best answer. Uh, Also, there is another method called tree of thought, where we break the chain of thought into multiple steps. So in the chain of thought example, what the process was divided into multiple steps inside the LLM, and LLM run that, execute that inside and give us the output. But instead, what we do here is we tell the LLM, I need the answer to this query, but you have to do that in a step-by-step manner. Just give me the result for the first step only. Don't give result for other steps. We can run a prompt like that and just generate the result for the first step. And we can do that multiple times and pick the best step. We can pick ourselves or again ask the LLM to pick one of the best one solutions, and we iterate that one until we get a better solution. So in that approach, also what we do is breaking down uh, long tasks to a set of smaller tasks. Okay, now our module can represent prompts, data, behavior, and also interconnection. We can integrate into applications and workflows smoothly this way. And we will go to more practical examples. Let's say you are running a customer support system. Uh, so customer comes with the query, I'm having trouble logging into my account. And without directly giving answer using an LLM, we try to get a personalized answer. So that's our goal. All the interactions that this system had previously are stored in a database. First, what we do is we extract all the information from the database that are relevant to this customer. And we are going to store those information in this Python class. It has interaction ID, customer ID, and the user query and the response that was generated by the system. And I load all the interaction of this user to this variable. and I write. So what I can do is I have the list of all the previous user queries with the answers, and to get a personalized answer, I can write a function with the query and the previous instruction to generate the response by analyzing the uh, previous interactions. And we can add COT to that as well to get a better result. But instead, what we do is we break that task into two separate tasks. First, we identify what are the relevant interactions for this query, and then we going to process going to the next part. So to get the relevant interactions, we write this function with the query and all the previous interaction, and this function will return the list of relevant interactions. I run that function with the user query, and it returned two interactions. One is with the query about forgetting password, and second one is also about password that user has complained is getting a message going called incorrect password every time. So we got these two interactions as relevant to the given user query. Then we generate the answer. We can write this function to get the user query and the relevant interaction and generate the string output as the answer. This was also run in GPT 3.5. So breaking down tasks into smaller tasks improve readability, reliability, and transparency because we know what's happening inside. In the COT examples, we don't know what's happening. The LLM comes up with all the steps and we don't have control. Now we know what's happening because we decide the step and the performance is going to be good. This is called prompt chaining, where we break down long tasks into smaller tasks and run one by one. This is good for debugging the problems if you have have a bug in the system, and also we can focus on improving stage by stage without taking the whole task into account. Here are some few more examples. Here you are running a store and you have to decide whether you need to change the increase the reorder level or decrease that one. For that one, I use three models. First, I have to store the product, which has product ID, name, currently stock, reorder level, and the reorder quantity. And I have supply class and sales data class. So this is the important class. It has the product ID, year, and the week number, and the unit sold in that year. Uh, in addition, we have the company have gathered knowledge over the past years about certain things and written them down in documents with Word files or text files. And uh, company needs to use its previous knowledge to answer these questions, these problems they are facing. So here in hard coding level, knowledge as a question answer uh, method. So the question is how the company should increase the reorder level, and as the knowledge, I have described the process of increasing the reorder level. To work with chain of thought, I have this reorder level class with reason. So this class is going to give a new reorder level, or it can have the same reorder level also, and but every time the LLM needs to have a better reason for changing the reorder level. They did. Uh, then to get the change reorder level, I have written this function. It get the product. and the sales data and the knowledge list of knowledge that we have. This time I will create one knowledge object. We can create a, product called apples with stock 30 30 apples in the stock, and sales data. I'm going to load data from a JSON. These values are random values, but if you look at the whole values, it's going through a upward trend. But if you to look at individual values, these are just random values. And I asked the LLM to generate the output, whether we need to change the reorder level or not. Here I pass the knowledge and sales data with the product, and LLM suggests to change the reorder level from 30 to 40, and it has reasoned that. This runs in GPT 3.5, and if we run that again without sending the knowledge, in 170 line you can see the knowledge array is empty. So we run the same thing, but this time without the knowledge. Here the LLM suggests to decrease the value 2 times. It suggests to decrease the new order level value, and 1 time it suggests to keep it as it is. So if we use GPT-4, actually always it says to increase the value because it understands better. But without using a newer model, we can use a model like 3.5 to get the output we need by just passing a knowledge to it, additional knowledge to it. So this is called knowledge prompting, where we pass a knowledge in addition to the COT instructions. And also we can use the LLM to generate this knowledge also, and it's called generated knowledge prompting. It was introduced in this research paper. You can take a look, and if you are using a separate LLM to generate the knowledge, we can use a data model like this and use a Marvin generate function to extract multiple examples, multiple knowledge examples. So in the previous case, the company had a set of documents with them with the information. What the company can do in a situation like this is having an encoder to encode all the knowledge documents they have into a vector. So these are type of encoders are called like word-to-vec encoders, and also embeddings. This process is called vectorization, and vectorized documents are stored alongside with these documents. And when a user comes with a query, it encodes the user query and compare it against all the vectors that we have stored and get the relevant documents we need. This is not a very new thing. This is actually very old thing that we use in NLP domain for quite some time, but it's new to LLMs. So it was introduced as RAC in this research paper. The same thing. If we run a query first, the query gets encoded and it compares against set of documents that we have in the storage, and get the best documents that are matched with the query. And to the LLM, we send the query and also the documents to get a better output. Yeah. So extending on that theory without using files. In this case, we use file. Without using files, we can get data from databases. To query databases, we can use vector databases that we can get data with queries with vectors. So it's also not very old thing. It became very popular with the introduction to RACs. And in addition, we can use search engines to get the knowledge we need, and we can use combination of everything also. In this example, we are storing a query, and we need to do some search action. For the search action, we have three options. We can do a web search, image search, or a video search. And we have written the function to segment the query. It will get the user query and segmented the given query into one or multiple of these search operations. Now the query is search for pictures of a cat and a video of a dog. If we call the segment query function with this query, it will output it will output data objects, two data objects, one with search query for image and one with search query for video. So as these are independent search queries, we can directly run them parallelly and get the results we need for the rank. We can extend this theory further. So in the COT, what we do is we identify steps and run them all, but instead this time we do it one by one, as we did in prompt chaining, and we need to send information at each step with the external source. So we are doing that as we did in knowledge prompting. Now we need to represent each step in our data model. For that, we are using this Python model. It has a thinking parameter where we store the thinking process of the LLM in this stage of generating this step. And we have an action field where it can have three actions: a person search action, a direct operation action, or a finish action that will terminate this thinking process. And alongside the action, we can send some action data and observation field. The LLM doesn't do anything to the LLM observation field. When we run the step using the execute method, it's going to call the person API and get the result and fill the observation field. So here, instead of calling, I just type the result in the input field and set it into the observation field directly. In the model configuration, this is a little bit of complex task, I send the example also. So in the example, I have a thinking like this, and the action the LLM suggests is person search, and who is Milhouse in Simpson. Since is the action data and observation, so it's saying that it's a television character. And we can send any kind of data with JSON schema extra field. We send the enum to explain the actions we have. So if we look at the actions, the model in the Pydantic data representation, we can't explain what each of these actions does. So I'm attaching them to the enum in the extra field. If the person search, we can perform a search about the person as the query needs to be given in the data field. And data operation is just addition or subtraction of dates. Finish will terminate the process, and you have to send the final result in the data field. And there's this function to get the next step. We will give the history of all the steps and the original user question to this function to generate the next step. And I have explained the process, and I said to the specific instruction to the LLM to not to mention any future steps, and also always generate data based on the history, don't assume anything. So we run this until we get a finishing point. And with as the question I asked, how old Tom Cruise when his first movie was released. So Python send that this to the LLM, and LLM thinks to answer this question, I first need to find out the date of birth and the release date of first movie. So it decided to do a person search action with the data, Tom Cruise date of birth. And I write the output, date of birth is July 3rd, 1962. And the second step, LLM thinks that it has the date of birth, but now I need the release date of the first movie in order to complete this action, this question of the user. And again, do a person search by asking what is the first movie of Tom Cruise. And I'm writing the output that it was a romantic drama uh, film released in 1981. Then, as in the third step, LLM thinks that it has got the birth date and the movie release date, and now need to do the calculation and do a date operation. And as the action data, it gives two dates. I send observation, and at the final step, it do a finish action, and as the action data, it send the results. So this was run in GPT 4 actually. So in this example, reasoning improves the accuracy, as we did in the chain of thought examples. We are asking for reasoning in every step. It improves the accuracy, and doing performance, doing it step by step, it's going to avoid mistakes as in prompt chaining and tree of thoughts. And we are sending external knowledge to further increase accuracy. And this method is released as React method, and is discussed in this research paper. As a summary, we learned how to use Pydantic to model data, and how to use Marvin with Pydantic to call LLM. And we uh, learned that a Pydantic model can represent prompt data behavior and also the interactions, but we need to have better documentations and variable learning. Then we identified that just querying data from LLM is not going to be enough, so that we introduce a chain of thought method where we ask for the reason from the LLM, and we run that multiple times to get a better answer. We introduce that with self-consistency, and all those methods without running, all those steps without running in a single query, we run it in multiple queries, and we introduce tree of thoughts and prompt chaining method. And lastly, just relying on LLM data is not enough. Because of that, we introduce knowledge prompting, where we send knowledge in addition to the prompt, and we ask LLM for the result. This data can be generated with external LLMs as well if we need. And we introduce the RAG, how to use RAG with the external documents we have. And if we have multiple data sources, how to modify the RAG to work with multiple data sources. And we combine everything to introduce this React method. So thank you for joining. It's the end of the presentation. If you have any questions, you can use the chat to ask.